seminar. If you haven't signed in if you registered for the class, sign in after the seminar. All right? With that, I'm turning it over to Dr. Reggio. Nick says some sort of sporting fact. Okay, and Dr. Reggio.
Okay, well this afternoon, Jennifer Pyle is going to be presenting her master's thesis work. She's been working in my lab doing studies of a new G protein coupled receptor, GPR18. Jennifer is from Ohio, and she got her bachelor's degree at Ashland University. And she got a BS in biology. And she came down here to UNCG partly because of her paper she read, right? A paper that she read that came from my lab. So she's been in the lab for 2 years. And what else to say about you? You love reptiles. She loves reptiles, and she's got some really spectacular ones. But take it away.
All right, thank you, Dr. Reggio, for the introduction. All right, so I'll just go ahead and get started. My project that I did for the past 2 years is on the identification of antagonist and agonist binding sites at the G protein coupled receptor, GPR18. And like Dr. Reggio said, I'm in the Reggio lab. So just a quick outline of what we're going to be talking about. I'm going to start with GPCRs, talking about their structure and their activation, and kind of how they compare to GPR18. And then I'll go into talking about GPR18 and its backgrounds. We'll start talking about my project in general, building the R-star bundle. The antagonist, their conformational searches and docking. The agonist, NA-glide, its conformational memories method, and its docking, and then I'm just going to sum it up with the conclusion. So GPCRs, GPR18 is part of the class A G protein coupled receptor of GPCRs. That's what I'll denote it as. These are categorized by 7 transmembrane helices, starting with transmembrane helix 1 in red, wrapping around the bundle, to transmembrane helix 7. There's always going to be a helix 8 on the C-terminus end that's parallel to the lipid bilayers that I kind of denoted by these dotted lines here. And we're also going to see an N-terminus at the extracellular end and a C-terminus at the intracellular end. So for terminology, you're going to hear me talk a lot about dihedrals. Specifically, I'll be talking about the omega dihedral that's going to connect that the peptide bond to amino acids. I'm also going to be talking about the chi-1 dihedral, that is the first rotatable bond of a residue off of an amino acid. So when I'm talking about, there's 3 different conformations that we're going to see these dihedrals adopt. That's going to be our G+, which is a negative 60 degrees, and I have examples down here. On the left, we have a phenylalanine, and like I said, in the G+ conformation, we're going to see it at negative 60 degrees, bending towards the helix. Then we can see it adopt a conformation, also known as a trans conformation, where it extends out at 180 degrees, and then it bending back in towards the helix at a positive 60 degrees, which is denoted as G-. So this is really important when I talk about the next slide, where we're talking about our toggle switch. So a toggle switch is a set of residues that has been denoted as the toggle switch because what happens is when an agonist binds, we see this toggle switch go through a conformational change. And this conformational change is going to cause a change in the binding pocket, which is going to ultimately change the receptor at the intracellular domain. When this happens, we're going to get signal transduction. So for GPCRs, this toggle switch is always located on the helix 6. It's located at a very conserved motif on helix 6 called the CWXP motif. And on that conserved motif, we see a tryptophan 648, and that tryptophan 648, along with another residue, for example, in the cannabinoid, the CB1 receptor with phenylalanine 336. What happens is we see these residues go from a G plus in an inactive state and extending out into 180 degrees into a trans position. And that's going to be what's going to activate that receptor. Now in GPR 18, we still see that toggle switch on the transmembrane helix 6 on that same conserved motif. However, instead of a tryptophan, we're seeing a phenylalanine 648. And along with that, we're seeing it interacting with histidine 652. And what happens in order for that phenylalanine 648 to go through a trans conformation, that histidine needs to move first. So that histidine is going to go from a G plus to a trans, and that's going to allow phenylalanine to go from a G plus to a trans. That's going to be what's activating that receptor. So when that toggle switch is tripped, this is going to allow transmembrane helix 6 to straighten out of the bundle, and it's going to straighten at this CWXP hinge region that we show here. So in an inactive state, I have a helix 6 represented in green, where we have that helix 6 kind of bending into the bundle, and it's held together by an ionic lock. When that toggle switch is tripped, that helix 6 is going to straighten out and kick away from the bundle. What that's going to cause is, like I said, the ionic lock to break, and that's what we see here. For example, in GPR 18 with the serine and an arginine that are in charge of that ionic lock, when helix 6 moves away from the bundle, that ionic lock is going to break. Ultimately, it's going to allow the intracellular end to open up, which is going to cause the C terminus of the G alpha subunit of the G protein to insert into the bottom of that bundle, and ultimately we're going to be getting a cell signal. During inactivation, an antagonist would be in the binding pocket, and it's going to be blocking that that toggle switch from going through a conformational change. So if you can imagine an antagonist, a ligand, sitting on top of that toggle switch, we're not letting that toggle switch and extend outwards. So what's going to happen, because that toggle switch can't go through a conformational change, we're going to see that IC end stay closed, that helix 6 is going to stay bent, and that ionic lock to stay intact. And we're not going to get a cell signal. For GPCRs, we usually see an arginine 350 and an aspartic acid or glutamic acid 630 that's going to be in charge of that ionic lock. However, in GPR 18, we do not see an aspartic acid or a glutamic acid. What we do see is that 3 residues away, exactly 1 turn up the helix, we're seeing a serine sitting right on top where an aspartic acid or a glutamic acid would be. And that's what we think is causing, is forming that ionic lock, keeping that receptor closed. A little background about GPR 18. It was first isolated for a mouse in 1996. It was part of the Human Genome Project. It's thought to be the abnormal cannabidiol receptor because a lot of the ligands that are turning GPR 18 on also turn on the abnormal cannabidiol that was found but was never able to be isolated. The GPR 18 role in the body is still unknown. However, we do know it has an effect on the immune system based on a lot of recent findings. GPR 18 is located in chromosome 13q32. That's the same region as the Epstein-Barr virus-induced receptor, EBI2. And that is an immunoresponse initiator receptor that's in charge of B-cell regulation. And we also see that GPR 18 and that EBI2 receptor have a protein, very similar protein sequences. So we hypothesize that they do play similar roles in the body. GPR 18 is also expressed in several locations in the body that deal with the immune system. For example, our peripheral blood mononucleocytes are white blood cells. Our lymphoidal tissues, spleen, and the thymus that deals with T cells. One of the most important studies that I thought helped contribute to shedding some light on the role of GPR 18's function in the body was the study that was done on channel catfish. where researchers infected channel catfish with a very fatal viral strain. And they saw that when these catfish were infected, we were seeing an upregulation in GPR18 expression. And furthermore, when we transfected these catfish with GPR18, we saw a 100% survival rate after 2 days compared to untreated fish. With immune-compromising diseases such as diabetes, AIDS, and cancers on the rise, there's it's a huge threat to public health and safety. This pattern of expression that GPR18 is showing us that GPR18 may play a role in the immune system, and it could be a valuable drug target for immune-compromising diseases. So now starting on talking about my project, GPR18 still has not been crystallized, and a former student in the Regio lab was able to create an inactive bundle based on the new opioid receptor. My project is a continuation of that project where I took the inactive GPR18 bundle and activated it. I did this by almost solely focusing on transmembrane helix 6. And what I wanted to do was have that receptor reflect a more active bundle. And by doing this, I needed to explore the different conformations of helix 6, because helix 6 needs to kick out in order for that bundle to open up in order for activation. So, like I said, we needed to find the different conformations of helix 6 and find something that represented a more active bundle. So in order to do this, because helix 6 has many dihedrals along the backbones and along the side chains, we needed a method that was going to calculate all those dihedrals, and instead of giving us millions of conformations, only giving us 180. So that's where conformational memories method came in. That uses Monte Carlo stimulated annealing random walk and the charm force field. This allows us to find conformations of very highly flexible molecules really easily. And this is done in 2 phases, an exploratory phase and a biased annealing phase. And ultimately, it was able to give us 108 conformations, but I'm going to talk a little bit more about the 2 phases. So the first phase of the CM method is the exploratory phase. In this phase, it identifies the region of conformational space for the torsional angles and bond angles. It does this in 18 temperature steps, starting at an initial temperature of 3,000 Kelvin. Each step, it drops down to a final temperature of 310 Kelvin. At each of these temperature steps, we're going to see 50,000 Monte Carlo steps applied. At each of these steps, 2 dihedrals and 1 bond angle are going to be chosen at random, and they're going to be rotated at a random degree. This torsional movement is either going to be accepted or rejected, and I'm going to talk a little bit about that process here in a second. But these accepted conformations are going to create a map or these memories that we're going to use in the bias phase. So in the exploratory phase, as we're dropping those temperatures down, we're seeing these populations of conformers begin to pool at roughly around 3 different degrees. It's going to be at negative 60, 60, and then we're seeing it curve up here at 180. And these are, like I said, the highest populations of these conformers that we're going to be seeing. So for the accepting and rejecting, as for both the exploratory phase and the bias phase, this process is done using the Metropolis criterion. As that bond is rotated, if we see an increase in energy, well, I should say, if we see a decrease in energy, automatically that rotation is going to be accepted. Now, if it is rejected, this is where the Metropolis criterion comes in. Because if the new energy is greater than the old energy, we still need to keep some populations of the high energy,